Hi everyone and welcome to this lecture. In this lecture I want to go over one-to-one and onto transformations. Now to refresh your memories from the last lecture we talked about linear transformations and we said the only way you can have a linear transformation if a matrix is involved and basically the action is done by matrix induction. That's very important because you can find out a lot of uh, things from that given matrix once you have the matrix. Now, first, we said the kernel of the transformation. Please watch the last video. We said is the span of the null space, and that's going to be in Rn. So for some vectors, tv equals to 0m, and the range of t we said is the range of t equals to the span of the call space to column space of A, and that's in Rm. So now I did show a transformation, so to kind of see what the range, the domain, codomain range, and the kernel are. So we go from Rn to Rm in this, and then Rm is the domain, Rm is the codomain, and somewhere in Rm you have the range, and sometimes Rm can be the range can be the entire Rm, and the kernel of t or cur of t here it's in Rn is the vectors that make the transformation 0. Now let's see what is a one-to-one or bijective transformation. So the definition, let's go over the definition. Linear transformation from Rn to Rm is one-to-one if and only if t of 1 equals to t of v1 equals to t of v2, then v1 equals to v2, or the only way two vectors from the domain have the same image in the codomain is for them to be the same vector. Let's see how that works. This is one-to-one because v1 gives t of v1, v2 gives t of v2, and v3 gives t of v3. This one is not one-to-one because v1 gives you t of v1 and v2 gives you t of v2, but these two are exactly the same thing. So therefore this is not one-to-one. So in this case, v1 is not equal to v2, but tv1 equals to t of v1 equals to t of v2. Therefore, it's not one-to-one. Now, how can we check that? There is a way to check that. It's called the kernel test for injectivity or one-to-one. So a linear transformation again from Rn to Rm is one-to-one if and only if the cur of t equals to the 0 vector. So uh, or you can write it like that. Or when you say Ax equals to has only the trivial solution. So now there is a proof for that. You can first assume that T of V1 to 1 and T of V1 to 1, that means we have that T of 0 is only the 0 vector. So T of V equals to 0 can only have V equals to 0 because it's one-to-one for the reason that I just stated. But this is a two-way proof. Conversely, we assume that T cur of T equals the 0 vector and T of U equals to T of V. So in linear transformation, we learned that T of U minus V is the same as T of U minus T of V. And in this case, we have both of them to be 0. T of u minus T of v equals to 0 and T of u minus v equals to 0. So obviously when we have that, that means u equals to v. So we see that in this case T of u equals to T of v and u equals to v. So therefore T is 1 to 1. Now let's do some examples. It's a fast way to find out if a transformation is 1 to 1. The first example, we have a transformation from R3 to R5. So basically the matrix is a 5 by 3 matrix, and we have that. Now, I also wrote R, which is the RREF of A here. So if you find the RREF of A, you get that matrix, and you need that all the time. Here we notice that we have X3 is the free variable because that's a non-pivot matrix. If we try to solve AX equals to 0, then we have x1 plus 5x3 equals to 0. That's from here. And x2 minus 2x3 equals to 0. Isolate x1, x2, and then x3 is the free variable, so you get that. So if we write the solution, so here we can write that vector at t times -5 to 1. And remember, that's curl of t, which is the span of the null space, which is going to be the span of this vector. So obviously this does not have only the trivial solution. So the above transformation is not 1 to 1. Let's take a look at this example. Same thing. These are kind of similar matrices. However, when you do the RREF of A, you get that. And as you notice, all the columns are here pivot columns. So in this case, we're going to have x1 equals to x3, x2 equals to x3, and that's 0. So AX equals to 0 has only the trivial solution. Therefore, T is 1 to 1. What's conclusion or the shortcut of that? If R, the RREF of A has non-pivot columns or free variables, we say, then you can say T is not 1 to 1. So each time you see a free variable or a non-pivot column in the RREF, that transformation is not 1 to 1. That's the shortcut of see if it's 1 to 1 or not. And if not, then it's 1 to 1, just like the above example. This one does not have any free variables, so therefore it's 1 to 1. And this one, the first one that we did, has free variables or a non-pivot column, therefore it wasn't 1 to 1. Now let's talk about onto transformations. Onto, we also call them surjective transformations. So the definition, again, if you have a linear transformation, it's onto or surjective if the range of T is Rm. So if that happens, then the transformation is said to be surjection or covering. Just remember, covering is very helpful to remember once you remember, because T hits all the vectors in Rm. Let's see the graphs of that. Now the first one is onto because the vectors in Rm, they hit the entire Rm. The range for this transformation is just Rm. Second example is not onto because the vectors just hit specific vectors in Rm, and that's the range. In this case, range of T is less than Rm, therefore it's not onto. A linear transformation is onto if the rank of T is M. So now how do you find the rank of T? Rank of T is rank of the matrix, which is the number of vectors in the call space or the row space. In this case, we're going to just look at the call space. So we have a transformation from R3 to R2 here. So if you find that's the matrix and the RREF is that. So now we notice that the range of T, which is going to be the span of the column space, is going to be the vectors corresponding to the pivot vectors in RREF. So we have that. So it's just one pivot column here. So this is the corresponding column, negative 2, 1. We notice we have one vector here, and the rank of T is going to be 1, and that's less than 2, which is M. So this is not on 2. Second example is pretty similar. However, we have 2 pivots here. So the corresponding columns are the first one and the third one. The range of this span of these 2 vectors. So therefore, the rank of T is 2, which is that number is M. So this transformation is on 2. Conclusion or the shortcut. If the RREF of A has at least one row of consisting all zeros, then T is not on 2. So just look at the RRFC. If the RREF has rows consisting of 0, this one does, so it's not on 2, and this one doesn't have 1, so therefore it's on 2. Now I put a note here for this is for 1-to-1, or kind of to see. I didn't put it on the top when I started this lecture, but as you see, this is another way of to see if it's 1-to-1. Here, T of 0 equals to 0. T of only 0 equals to 0. So this is 1-to-1. But in this case, not just T of 0 equals to 0, because we have other vectors too. So this is not 1-to-1. Please watch this lecture 2-3 times and try some problems on your own. And I'll see you in my next lecture. Thank you for watching, and have a great one, everyone.